Once upon a time, last semester, I believe, we learned how to find the arc length of a rectangular curve, and it was using the derivative of the function that we then squared, and then we added 1 to it, and then we took the square root of it. At first glance, it doesn't look like it makes any sense, but when you watch the derivation, you realize that it's really just the Pythagorean theorem / distance formula, and what you're doing is you're adding up little bitty linear approximations of the curve, not tangent line approximations, but like I guess secant lines, right? Connecting 2 points that are on the curve. And then of course the integral causes us to take the limit of this process and get an exact value. So it's basically applying the distance formula to an infinitely large number of infinitely small little line segments. We're going to do the same basic thing here. The difference is we've got two different equations, one for x and one for y. They're not bunched together like we're used to seeing in rectangular world. In the parametric world, we have two different derivatives, one for x, one for y, so we just take the Pythagorean theorem of that, right? So this is very similar to this equation. And you can review the derivation of that original equation and see if you can come up with the derivation for this one as well. It's a good exercise. But the formula is perhaps not too surprising, so let's just go ahead and jump into it and see what we get. So we're going to try to find the complete length, the length of the complete curve here. Well, again, this is something we're already familiar with, right? We know that this is, I can't draw a vertical line. Better. We know this is a circle. Oh my goodness, now I can't draw a horizontal line. We know that this is a circle whose radius is 4. And it goes around the origin. So if we're interested in the length of this curve, we're really asking for the circumference of the circle. We already know the answer to this question. Again, we're going to use the calculus to verify this, but of course the answer is 2 pi r, where r is 4. So let's take a look at this. First of all, we have to figure out what are the t values. We're starting from a going to b, of course. T is running the show here, right? dt is our differential there. So as we kind of played around with before, we realized that we started at t equals 0 over here, and we went around the circle to t equals pi over 2, and then over here to t equals pi, and then around here to t equals 3 pi over 2. These should look kind of familiar, right? And then finally we end up here at t equals 2 pi. It's not always going to line up this way, but because these are both positive and cosine is with x and sine is with y, then yeah, these are the unit circle values that we're comfortable with. So that means that to start at t equals 0, we're going to complete the entire path when we get to t equals 2 pi. That's our a and our b values. So the complete curve is completed when t goes from 0 to 2 pi. We could do from pi to 3 pi, or we could use 0 to pi over 2 and assume that everything is symmetrical, so multiply that by 4. There are lots of different ways we can do this problem. But anyway, we're going to go ahead and just do it the most straightforward way. Dx dt is negative 4 sine of t, negative 4 sine of t, and we're supposed to square. This is your a squared plus b squared business, right? Same thing with the dy dt. We're going to get 4 cosine of t, so we're going to put 4 cosine of t, but we're going to square that, and we'll take the square root of that whole thing. And the variable of integration is t. All right, so this might be a little scary until we realize, wait a second, hold on. We're using the Pythagorean theorem with our trig expressions. This must be our favorite trig identity. And of course it is. We've got the square root of 16 sine squared of t plus 16 cosine squared of t. So if we factor out that 16, then we end up with the easiest thing in the world, which is 1, right? That's our favorite trig identity, so that's equal to 1. So we really just have the square root of 16 in our integrand. But the square root of 16 is the easy value of 4. So we'll integrate 4 dt. Well, the derivative of 4t with respect to t is 4, so 4t must be the proper antiderivative. We'll evaluate that at 2 pi and at 0, and oh my goodness, we're going to get 4 times 2 pi minus 4 times 0. We're getting the answer we already knew we were going to get, 8 pi, which is 2 pi r. Isn't it great when things just work out? All right, now of course we're not going to be doing circles too often with this method because we have the simple 2 pi r equation that works every time. Comes straight from the definition of pi, by the way. But what about our fun little loop-de-loop curve that we looked at before? The original question asked from -1 to 2. I might decide to change that because, honestly, from t equals -1 to 2, let's do this. This is kind of fun. We'll go from A to B, and we'll see if we go from -1 to 2. That's kind of fun to see how that thing grows, isn't it? I suppose we could do that problem, but I'm not so wild about that because those seem like kind of random points. I think I'm going to change this. So I'm going to change it to find the length of the little bitty loop right here. Now that seems to be like a more fun question to me. You can do it either way. It doesn't matter. You're just changing the bounds of integration. But in order to figure out what the length of this loop down here, this very small loop, is we're going to have to adjust these t values. Right now we have too many t values. So maybe I'll bump this lower one up from -1. You can kind of see that as I bump that up, we're getting rid of some of this stuff. And if I bump this down, we're getting rid of some of that stuff on the top. So we're going to try to zoom in on just the part that we care about, the part that I've decided we care about, which is that little loop-de-loop here. So we'll keep on bumping up that smaller one. And it's looking like t equals 0 is where this loop starts. And it's looking like t equals 1 is where this loop ends. In fact, if we know that it's the point 2 comma 0, and we do because we're looking at it, then we can just set the x value equal to 2 and the y value equal to 0, and we can solve, and we can see that the solutions in common are 0 and 1. Okay, this is a very tough problem to do without the aid of a graph. So anyway, let's just play around with this though. So now we've figured out that if we go from t equals 0 to t equals 1, that'll trace out that little loop. So let's change this. Let's change this to 0 and 1. It just makes me a little happier, that's all. So s is going to equal the integral from 0 to 1, the square root of, let's see, so we have to do something squared plus something else squared. It's not a bad idea to write it out like this, just so we don't forget to square things. Remember, this is just the Pythagorean Theorem, so that's a familiar formula for us. Derivative of this goes in the first parentheses. That's going to be 2t minus 1. Derivative of this is 3t squared minus 1. And this would be the point in time when I would say set up but do not solve. And that would be your final answer. Alternatively, you can go ahead and pull out a calculator and get a decimal approximation for this. I'm not very interested in spending a very long time trying to figure out obscure integration techniques that may or may not even work for something like this. So let's just go ahead and go back to Desmos, and we're going to integrate int from 0 to 1 of the square root of something squared plus something else squared dt. What were those somethings? Well, they're the derivatives of what's on the top here, right? This was just 2t minus 1, 2t minus 1. And this was just 3t squared minus 1. 3t squared minus 1. And there we've got our answer. It's a little less than 1. I could buy that. We go about half of a unit to get out to this farthest point, somewhere around there, and then half a unit to get back. There you go. So 0.928 appears to be approximately the right answer. 0.928 units is the length of that loop-de-loop.